Okay, good afternoon, everyone. Thank you for joining this tutorial. So this tutorial is about LLMs are human-like annotators. So the presenters are Monica, so myself, Subbareddy, and Manish Gupta. So Monica and Manish, they both are presenting remotely, and I'm presenting in person here. So if I so when Monica and Manish, so when they are talking, so they give their introduction. So myself, so I'm Subbareddy. I'm a postdoctoral researcher at Technical University Berlin. And we'll go through the tutorial now. So this is the agenda of the tutorial. So Manish will present, so in the next 1 hour, he'll talk about introduction to LLMs and recap their capabilities. And in the next 30 minutes, like in the second part of the tutorial, so he'll talk about generating annotations for NLP tasks using LLMs. Go ahead, Manish.
Okay, thank you, Subba. Welcome, everyone. And, we apologize for the odd setup, but hope you can still hear me okay. We are about 10 minutes late, but that should be okay. We will still stop when it's coffee time. Okay. So as Subba mentioned, I'll be covering these two topics. Post that, Subba will basically...
Manisha, can you please share your screen?
I am sharing my screen, Subba. Can you see the screen?
Sorry.
Yeah, it's visible for me as well. Yeah.
Right?
Yeah.
Okay. Awesome.
Yeah.
So then Subha will talk about these two other topics, which is about benchmarking LLM annotations and human annotations and evaluation of LLM generated annotations. And then finally, Monica will talk about more implementation aspects around auto label tools to label reasoning datasets and in NLP datasets. And lastly, she will talk about how can you overcome hallucinations in these LLM annotations and some future trends. Okay. So let's get started with part one. Part one is more like a sort of a revision. It's sort of a discussion about how what are the various LLMs, what are they capable of, and so on. So as to basically understand their skills or their capabilities, which make them usable for generating annotations. Okay. So large language models are what we have now as a follow-up in the deep learning field. So deep learning field has been going on for decades, and people started favoring deep learning more recently, starting from 2012, because they realized that unlike standard machine learning, you don't really need to do feature extraction. The deep learning models basically do the feature extraction and the classification both together. Right? And that has led to significant progress in deep learning across various domains in NLP, in computer vision, and so on. Specifically in NLP, yes, people started small from RNNs, LSTMs, those kinds of sequence-based models, which had very small number of parameters. But over time, people started moving on to more mature models like encoder-decoder models, attention-based models, transformer-based models. And then since around 2017, 2018, all we have now is around is basically transformer-based models and lots of models based on transformers, like transformer encoder models, decoder models, encoder-decoder models, like BERT, GPT, T0 bar, T5, and so on. More recently, the paradigm of learning has sort of changed from fine-tuning to in-context learning, and that has given rise to these prompt-based models like GPT-3, Instruct GPT, and GPT-X versions, as we'll talk about in this tutorial. So GPT-3 basically believed in this very, very simple principle that humans do not really require large supervised datasets to learn most language tasks. So therefore, the idea is to basically have one model which can perform multiple tasks. You should not really be needed to fine tune the model for a new task. The model should be able to learn any new task at inference time. And that is what is basically then called as in-context learning. So in-context learning. So GPT-3 basically transformed the field by saying, hey, if we won't do fine-tuning anymore, let's basically start doing in-context learning. Zero-shot in-context learning, if you basically just give the task to the model and ask it to perform the task on an input. One-shot in-context learning, if you basically give the task to the model and also one example of how it is done, and then you ask the model to do that task. Or few-shot learning, where you basically give the task description, a few examples to tell it how, to tell the model how does it work, how the task works, and then lastly provide the input. Now, over time, of course, folks took this GPT-3 kind of model, and then they said, hey, GPT-3 is great, as a more of a generic model. So you can give it a prompt and it can give you a response, and awesome, 175 billion parameter model, very large model, and that's great. But can we make it better? And therefore, the recipe which is followed these days is to not just use the pre-trained model, but also do two more steps to it: supervised fine-tuning and then reinforcement learning. Supervised fine-tuning basically typically means that you get a whole bunch of labeled, you get a whole bunch of demonstration data, or sort of questions kind of data set, or a prompt kind of data set, and then get it labeled by humans, right? So in other senses, it is also called as instruction tuning, or chat, prompting for chat following, all different names for the same thing called as supervised fine-tuning, right? You basically collect a whole bunch of prompts. You basically ask humans to actually label them, and then you take your pre-trained checkpoint, let's say GPT-3, and you fine-tune it using the supervised fine-tuning data. It just turns out that this model now becomes much more capable of following human instructions. However, there's still a gap in between between a way a human follows instructions versus this model follows instructions. And to be able to fill that gap, people come up with reinforcement learning, where the idea is that typical reinforcement learning algorithms require you to first train a reward model, right? So reinforcement learning is basically a different variant of machine learning, where the policy or the model sort of takes an action, and then gets a reward for that action. So in this reinforcement learning kind of a setup, there are iterative steps. As you can see, reinforcement learning part is sort of iterative in nature, where you essentially build a reward model, and then you sort of apply reinforcement learning to update your original model, which is also called as a policy model. Okay. So what do you mean by reward model? So the idea is that you take this supervised fine-tuning checkpoint, you actually give it a question like this: explain the moon landing to a 6-year-old, get like 4 different answers from it. You ask a human to preference label it. So in the sense that tell which one is better compared to the other response, right? And that basically gives you a preference ordering over these responses, which is what is used to train a reward model. This reward model, the goal is basically to be able to take a few to be able to take a response and then give a reward, saying, hey, this particular response is good or bad, and entire range of those. Okay. Now, the reinforcement learning, what it does is to really take a new prompt, like write a story about frogs, and then it basically uses your current model so as to be able to obtain responses, uses reward model to figure out whether the response was good or not. And if the response, depending on whether the response is good or not, it gets a reward. The reward is used to update the model using some reinforcement learning algorithm. For example, PPO is a popular reinforcement learning algorithm. There are many others now, like DPO, which are also used for reinforcement learning, or GRPO as popularized by DeepSeek. Right? So, over time, people have done a whole bunch of this stuff. And so now people train models with trillions of parameters, which are pre-trained, and then, pre-trained with clean data. And then people do sometimes mid-training as well, which basically means expanding the context length on which these models can perform. And then they also do post-training, which is basically what you saw: supervised fine-tuning and reinforcement learning. And then the models have become so awesome that, yes, you can actually use them to get labeling done. So at Microsoft itself, for the past few years, we have been using these models to get labeling done, unlike previously, the way we used to get it done via humans. So getting labeling done using models is cheaper. So it reduces the dollar cost versus human labeling, right? It is faster because you basically get responses way faster than you would get from from humans, especially for languages other than English, right? Agility, so you have big developer savings because you do not really need to now create those interesting UX-based hit apps, as they are called, human intelligent task apps, right? But of course, you have to spend some time in prompt engineering, writing the good prompts, right? Quality, yes, you basically typically get higher label quality. Okay. So of course, this doesn't come for free. So of course, you have to do some good job in prompt engineering. You have to basically come up with a good task description, good examples. Coming up with multiple prompts and then doing ensembling in some ways also helps. And the interesting part is that, unlike humans, right here, you can actually also get good quality generated output. So you can actually control for output length. You can control output language. You can control output style as well. Right. So that's that. And people have been using these kinds of things for a whole bunch of NLP tasks. These kinds of models now have become so awesome. All of you use ChatGPT, so I'll not really go into details. But yes, I mean, unlike extractive summarization, which we could do in olden times, now you can actually do nicely abstractive summarization. Unlike standard just factoid question answering, like what is the capital of Italy, right? You can actually do more interesting things, like answer complex questions for which there is no answer on any single web page, but you require intersection of evidence across multiple web pages. You can, of course, support machine translation in a much more natural manner with a very high quality across 100 plus languages. You can automatically now add creatives. You can actually solve machine reading comprehension problems. And even the complex questions, not just factual questions or not just questions which have direct answers in some phrase in the passage, but more of thoughtful questions, reasoning related questions, and so on. Okay. You can, of course, solve various kinds of reasoning problems, common sense reasoning problems, spatio-temporal reasoning kind of problems, mathematical reasoning problems, logical reasoning problems, and so on. So this is an example of an English reasoning problem. Sometimes it's so interesting how these models can come up with very good answers. For example, in this case, the question basically asks, what is the right way of using adjectives before a noun? And to my surprise, I actually did not know that there is a standard order. And the model basically first comes up with the English rule, which dictates how the adjectives should be organized before you put them, when you put them before a noun, and then really comes up with the correct answer why a particular option, which is given here, is correct compared to the other one. Okay. So large language models have been leading the way significantly in the past 5 years or so. In Feb 2023, an interesting thing happened. And basically that was Meta coming up with this open model called as LLaMA. Until then, large language models were primarily being developed by the big Bs, big companies like OpenAI, Microsoft, Google, and so on. But since 2023, what people have started coming up is small language models. So Meta came up with LLaMA, and then Meta came up with LLaMA 2, then LLaMA 3, LLaMA 3.1, and so on and so forth. But then people also came up with other kinds of small language models like Alpaca, MPT, and 5 series from Microsoft, and so on. Okay. So these small language models are way smaller than large language models. So of course, there's no standard definition for this, but I would say anything beyond, let's say, 20 billion parameters is more like a large language model. But these small language models are very small. They are primarily something like 7 billion parameters, 10 billion parameter kind of models. GPT kind of models, GPT-3 was 175 billion parameters, GPT-4, GPT-4o, GPT-o3 mini, and so on are rumored to be, trillions of parameters using mixture of experts kind of a setup. They are like probably tens of trillions of parameters. Okay. So this is a key slide or a sort of a very summary slide about small language models. As I was mentioning on the previous slide, when Meta came up with LLaMA, others could basically follow suit. So therefore, yet another company came up with Falcon, and then Microsoft developed this interesting thing called as low rank adaptation, LoRa, which many of you might have used, LoRa, QLoRa, and its multiple variations, right? What LoRa did, was to basically allow fine-tuning of these fine-tuning of these small language models to be of the same capability or close capability to large language models, but with very, very small costs. Now, the costs are in terms of training costs, training RAM costs, and also the disk cost to save the model. Okay. The interesting part is that until June 2023, unfortunately, academia or startups or people who do not have too much money, couldn't really be in this game. But thanks to LLaMA, they actually had a pre-trained checkpoint on which they could fine-tune. And thanks to LoRa, they could actually fine-tune because they did not really need to load the entire model and do full fine-tune and so on. But they could actually live with, low-rank adaptation. Again, read up LoRa if you do not know how it works. Okay. But what people started doing, groups from Stanford and groups from Berkeley and so on, they started sort of taking the pre-trained LLaMA model and instruction tune it by using data gathered from GPT 3.5 or GPT-3. You had a model which was performing way better compared to the original LLaMA itself. Okay. People started coming up with better ways of tuning. So essentially, for example, at Microsoft, we developed something called as an ORCA model, where you would do explanation tuning. Now, this is very much similar to what is called as chain of thought prompting, and I'll basically talk about that very soon. But people started coming up with these various ways of prompting and tuning their models so as to come up with improved small language model versions. Now, the small language model variants, people try to do a sort of a race, right? I mean, there's a race for large language models getting better and better ones. Small language models, there is another race where you basically try to get as close to the complexity that the large language models can handle. Okay. Meta also came up with LLaMA 2, and this time Meta did not just release the pre-trained checkpoint, but also the RLHF checkpoints, the reinforcement learning based checkpoints. Um, uh, and this is also the time when people started thinking a lot about how to make models more safe. Helpfulness is one thing, but then safety is yet another, and that's what people started stressing on. Microsoft came up with ORCA 2 with better ways of sort of fine-tuning the model, supervised fine-tune the model, and therefore better results. There's yet another company, Mistral.ai, which basically started European company, which basically also came up with Mistral 7 billion parameter models. All of them following the same standard transformer decoder architecture, by the way, right? But Mistral came up with its own pre-trained checkpoint right from scratch, did not really follow LLaMA. Okay. And then Mistral came up with its mixture of experts version as well, called Mixtral, which was very comparable with the initial versions of LLaMA. And well, Meta has been continuously working on better and better variants of LLaMA. And same in similar senses, Mistral.ai has been coming up with more refined versions of Mistral. On the other hand, Microsoft has been coming up with more refined versions of Phi as well. So Phi 1, Phi 1.5, Phi 2, Phi 3, and more recently Phi 4 as well. Right. So the interesting part is that in this small language model world, LLaMA 1, again, I'll not, of course, read through the entire slide, but LLaMA 1, people showed was pretty good in terms of various tasks, whether it is common sense reasoning, question answering, reading comprehension, or other tasks like mathematical reasoning, code generation, or basically on a bunch of tasks, a bunch of around 50 tasks, which are a part of the MMLU benchmark. Okay. LLaMA 1 was available in 4 different sizes. Meta released it in 4 different sizes. The 6.7 billion parameter model is actually the most popular one and the one that basically got everyone very excited because it was small, could be loaded easily in a 32 GB GPU machine, and people could fine-tune experiment with it. And the beauty is that in many of these tasks, these small LLaMA models were actually way better or equivalent in comparison to large language models like the GPT-3 175 billion parameter model or the Palm model from Google, which was 540 billion parameter model. Okay. As I was mentioning, Meta then came up with LLaMA 2, and this time they did not really bother just about helpfulness, but they also bothered about safety. And they basically showed that their models are not just the best small language model that one could have, but also safe, right? But also safe. LLaMA 2 models were almost the same sizes as the LLaMA 1 models, but with a larger context length. In fact, at that time in 2023, about 1.5 years back or about 2 years back, there was no phase called mid-training. So people basically therefore had a context length of just 4K. Nowadays, people do this mid-training where they try to enlarge the context length on which the size of the inputs on which the model can perform. And it's very common to actually have models which support, let's say, 16K context length, even the small language models which support 16K context length, or large language models like Gemini, which can support like 1 million tokens context length as well. Right. As I was then mentioning, yes, I mean, Meta then came up with LLaMA 3, and they clearly showed that they're, and they, of course, released both the pre-trained checkpoints as well as the instruct checkpoints, right? And they basically showed that Meta LLaMA 3 is sort of comparable with Google's Gemma models, which are also 7 billion, or Google's Gemini Pro 1.5 models, which are much larger, Okay. After that, LLaMA came up with 3.2, and LLaMA 3.2, the interesting part is that it is multimodal as well. So not just it's basically better compared to the previous LLaMA models, but one, it is smaller. So the smaller models, basically there are 1 billion parameter checkpoints, 3 billion parameter checkpoints, and so on. And second, the slightly larger checkpoint, which is basically 11 billion parameter checkpoint, can actually support multimodal tasks as well. So you could therefore compare it with some multimodal support kind of models like Claude 3's Haiku model or GPT-4 Mini, and then basically try to figure out how well it is performing compared to those really large models on these multimodal tasks. On some of these multimodal tasks, it could actually beat really large models, while being, while there's a lot of room to cover if you really compare it with these large language models like GPT-4 Mini. Okay. So, of course, GPT-4 series has been doing great by itself. So if you basically are okay using models as APIs, then you could actually use GPT-4 or GPT-4.5, which was released very recently, where the model can actually perform really, really well. So this chart actually shows to you how across many, many exams that you can see on the x-axis, the GPT-4 model is able to actually obtain scores which are very, very close to the toppers, right? So essentially, human level performance on majority of these professional and academic exams. In fact, it could basically pass a simulated version of the bar exam with a score in the top 10% of the test takers, right? So isn't that awesome? Similarly, you must have heard about Sam Altman claiming that they will come up with models which will be better than the best software engineer in terms of coding various problems on lead code and so on. Okay. Now, there are more examples of how well these models are doing, but I won't bore you with things that you can, of course, try out yourself on ChatGPT, right? So you can look at these slides later and just sort of think through the kind of reasoning abilities that these models have had, right? And the motivation to show these reasoning abilities is not just to show off or rather, make it so boring. Hey, I do this with ChatGPT every day, big deal, right? But the idea is to sort of consider this as a very strong motivation to why you can use these models in today's world to do a large variety of annotation tasks. For example, not just those text-based tasks, but also these picture understanding or chart understanding kind of tasks, right? So data interpretation kind of tasks where you have these different bar charts, pie charts, tables, and you want to sort of interpret and come up with answers. Typically, these kinds of analytics tasks have required a whole bunch of human labeling, but now these reporting tasks that several people do, analysis tasks, all of them can be now automated thanks to these large language models, and you can actually obtain nice annotation data thanks to these large models. Right. They can do good image understanding. They could basically do good, geometric reasoning, information seeking about objects. So they actually have a very good world knowledge, or they can actually connect now, thanks to retrieval augmented generation, to latest and freshest world knowledge, sometimes enterprise-based knowledge as well, hidden knowledge, and therefore come up with really, really awesome responses. Multimodal reasoning as well, right? These models now can actually understand humor. So I remember myself working on this comics-based task where we were basically trying to come up with the next utterance in a comic strip. At that time, we were working on this about 2 years back, and unfortunately, models were not really very good at coming up with humor. But now, humor is actually encoded in these models. It basically understands what humor means. It can explain humor, generate humor, these kinds of models, right? Fortunately, they can also do common sense reasoning in a multilingual setting. So if something works in English, highly likely it works on most of the top few languages on the web. And clearly, well, these models are also useful not just in standard NLP, but also in code generation. So people have used them. We use them in GitHub Copilot, right? And for various kinds of purposes, various kinds of code-based tasks. Not just a standard simple math, school level math. They can actually solve interesting calculus problems as well, or do video understanding. Given this video, it can sort of explain what could this person do to improve their technique, acting like a coach in that senses. Right. So the motivation to do this was to basically give an introduction to large language models, a very quick summarized introduction, which hopefully serves as a great motivation to why these models could actually serve as automated annotators for various kinds of NLP tasks. However, there are two problems mainly, when you try to use these models for doing NLP tasks. The first problem is that, yes, the large language models work great, but then, they are very large. They're too expensive. Also, maybe I don't want to put out my data to those models. I have private data, maybe users' data, partners' data. I don't want to share it with OpenAI, right, or with Claude, so as to basically Anthropic, so as to basically get the labeling done. So how do I get that done? So maybe I need to train a small language model. How do I train that? Right. Second, quality. So if I were to use the small language models, I basically face this challenge of poor quality, right? So how do I basically improve the quality of the annotations that I can get from these large language models or small language models, whatever you want to consider for your own setup, okay? So therefore, in the second part that I'm going to spend like next 30 minutes on, I'll talk about are large language models good annotators by themselves? Are they? Let's basically question that as well, right? How can we get better annotation accuracy from large language models or small language models, right? How can we do it better? Okay. How can we use large language models to generate samples and then label them? So, having a lot of unlabeled data and being able to get that labeled is one problem, but then not having any data at all, just generating data to label as well is another problem. Okay. And the fourth thing that I'm going to talk about is how do I generate diverse and attribute-specific data sets. Now, everyone tells me in the pre-deep learning world, people used to train these machine learning classifiers, and they used to deal with this unbalanced data set problems and so on. Now, this imbalance in the data sets exists even today. There is bias, right? Now, how do I sort of handle that imbalance? And therefore, ask these models to generate data which is balanced, and then ask them again to just label them, right? Yeah. So the other things that I'm going to discuss in the second part. Let's get started. So are large language models good annotators? Now, of course, within Microsoft, we did several internal studies, but then there are these public studies as well. So by the way, if you have not noticed so far, each slide basically has a link to the paper where you can read more details. Right? So, these folks basically did the study where they were basically looking at a task where, workers were being asked to tell whether a tweet is relevant about content, whether a tweet is about content moderation or is it a separate task about politics, right? So there are these political tweets and they're trying to figure out some tasks on content moderation for tweets. So they try to evaluate this task across 5 different aspects: relevance, topic detection, stance detection, and so on. And what they found, of course, we'll not get into details about each of these. These slides are for reference. You can look at them later, right? But what they found is super interesting. ChatGPT is better than crowdsourced workers by 25%. Okay. In fact, they found that ChatGPT's inter-annotator agreement exceeds that of both crowd workers and also trained annotators. Okay. And cost, well, ChatGPT is less than $0.003 per annotation, which is 30 times cheaper than Mechanical Turk workers. Okay. Similarly, in another study, which Subba and Monica and I are a part of, right, we basically use these models to do very complex annotations. So we basically take long Reddit threads, and if you have been on Reddit, you would know how long these are, right? And we basically take top two authors on these threads, take any thread, take top two authors. And then for those two authors, we want to get a very, very interesting subjective task done. And the task is figure out the user's stance, okay? And figure out whether the user is dogmatic or not, okay? Now, what do I mean by that? So given a particular author, I want the model to tell me whether, what is the stance of the user. So is the stance, and given a topic, so here's a topic, capitalism versus socialism, is the stance of the user strongly against something, somewhat in favor, or essentially somewhat against that, and so on. So there could be like 5 different stances, 5 different kinds of stances. Okay. Similar, so it's a 5-class classification problem, but a very, very interesting and subjective one, right? If you give it to humans, it's very complicated to get it done because the threads are so long. Figuring out whether a user what is the stance of the user, very complicated. Okay. Similarly, dogmatism. So given a long thread, figuring out whether the user is basically flexible, deeply rooted in their arguments, open to dialogue, firm, very complicated to do it for humans, but we are able to get it done via these LLMs nicely. In fact, we found that the inter-annotator agreement between these LLMs was very, very comparable to inter-annotator agreement between humans. Okay. In fact, on a small data set, we actually found that there was a very good agreement between what the humans labeled and what the LLMs labeled. Of course, it may not really directly work with just one LLM. So actually, we tried in 2 different LLMs, Mistral Large and GPT-4, after choosing across multiple of them. And then we also tried different settings, 0 shot, 1 shot, few shot, and then we voted over them. So this voting is actually better than voting over human labelers. There are more results in the paper And of course, I'm not saying that everything is green here. Of course, the LLMs do make mistakes. For example, we told them to come up with labels for a particular user ID, and it turns out, well, it hallucinates user IDs as well sometimes. We also told it, hey, basically, in the JSON schema, give us only few things. And well, sometimes it really does not follow the JSON schema and spits out some other keys. Okay. Yeah, I mean, there are failure cases, but the good point is that there are very few failure cases, right? And it works nicely, okay, most of the times. Well, some people also have tried selective annotation. So and then try to get those selective annotations done from large language models and then train a small model. Okay, so the idea is in step one, you basically use some large labeled data which you might have, but you also have, let's say, a very large unlabeled data. You use a large language model like GPT-4, but you select very carefully what data to label because you do not want to use a whole bunch of OpenAI API call budget. You get a small amount of labeled data, and then you use it to basically, either retrieve those samples in the RAG kind of setting or use them to fine tune a smaller model. So people have done those kinds of things as well, and that is how they have less small, less dependence on very large models, but then larger dependence on these small models that they can further fine tune, or essentially just use in the RAG setup. So, and then there are ways, how do you basically select these unlabeled samples to be annotated by the large language models? Okay. In a very recent study, this is basically 2024, just last year, in a very recent study, people tried to actually do this very rigorously. Can LLMs be used instead of human judges? And they experimented with like 20 different NLP data sets, evaluated 11 different LLMs, 11 different large language models. And you see some of those large language models here, some of those here on the columns. What you see on the rows is basically these 20 different NLP tasks. Some of these tasks are categorical. Some of them have graded annotations. So, more like numeric in that senses, rankings and so on, right? So some tasks could be on both sides as well. Right? And what do you see? What are their main findings? So their main findings is that they find that for some tasks, models are really good, but for some tasks, models are not that good. In fact, models are reliable evaluators on some tasks, but overall, they do display a whole bunch of variance. So a whole bunch of variability depending on the property being evaluated. What are you trying to evaluate, right? The expertise level of human judges, of course, if you compare with like average humans, maybe the models are great. But if you compare the expert humans, not so good, maybe. Yeah. And whether the language, the input data which was used for labeling is human generated or model generated. Okay. So therefore, they basically leave with a very interesting impression that, hey, when you're using LLMs as annotators, please use them, please carefully validate the quality with some human judgments before using them for a downstream task and application. Okay. So now the idea is, how can we get better annotation accuracy for LLMs? Most of you would have heard about this chain of thought prompting thing. It came up like about 3 years back in time, where the idea is that so the idea is as follows. This is the standard prompting example, the chain of thought prompting example. In a standard prompting example, in a few shot setting, you basically give a word problem, math word problem, give the answer. And then you give it another problem, and then you tell it, hey, come up with the answer. Okay. But in a chain of thought prompting setup, what you do is to give the model a question, an example, right? So question, and then basically a little bit of an explanation called as the chain of thought. It's basically a series of intermediate natural language reasoning steps that finally lead you to the output, okay? And then essentially you give another question to the model, and hopefully you basically hope that the model will basically generate a chain of reasoning and also an answer. And more likely, than not, it'll basically come up with a better answer, a more correct answer. Okay. So chain of thought prompting has several benefits. It basically allows the models to decompose multi-step problems into intermediate steps. It improves interpretability. If I was a student and trying to solve a math word problem, I would clearly want the intermediate steps as well, not just the final answer. Okay. And then the interesting part is that with chain of thought reasoning, even smaller models could actually become as good as larger models, or larger models basically achieve state-of-the-art performance on some tasks, right? On some of those tasks. So the idea is that, yes, chain of thought prompting improves the kind of annotations one can get from these large language models. Chain of thought prompting has a problem. It requires labeled examples of the reasoning process, right? So to do chain of thought reasoning, as I showed to you a few short examples, you need labeled examples of the reasoning process, okay? So zero-shot prompting, the problem is you get low accuracy. Zero-shot COT, again, low accuracy. It doesn't really generally work if you don't do few shot. You do few shot COT, that's great, it works, but then it basically requires those few shot labeled examples for every task you want to get done. Can you basically ask the model to generate those few shot examples as well? Now that's awesome, right? And that is what is called as analogical prompting. The idea is that you basically tell the model, here is my math word problem, and this is how you should solve it. You basically sort of come up with a meta suggestions to the model, telling it, hey, first, basically think about relevant examplers. So think about chain of thought examples, right? And then you solve the initial problem itself. So here the model is basically doing example generation, chain of thought prompting based example generation, and then it's solving the problem. So this is called analogical prompting, and it's a great idea because it takes away the burden of coming up with labeled exemplars of the reasoning process. Okay. They expand on this idea by saying, hey, let the model not just do two things, coming up with relevant examples and solving the initial problem, but in fact, let it also try to solve a more generic, try to solve it in a more generic manner. So let the model first figure out what kind of knowledge it would need, like what kind of branch of science or, kind of topics, core concepts it will need to solve this problem, and then come up with few short examples and then solve the problem. And people have sort of observed that this kind of a thing gives you really good results on various kinds of tasks, as you can see here, mathematical tasks like GSM8K or math, and also other kinds of reasoning tasks like temporal sequences, reasoning about colored objects, word sorting, and so on. Okay. Now people expanded on this chain of thought reasoning to another kind of a process called as memory of thought. So memory of thought is basically like chain of thought, but then combined with RAG kind of a setup in some ways. Okay. So the way it works is as follows. Offline, you take a whole bunch of large unlabeled data. You ask your large language model, to basically generate chain of thought. Of course, also generate answer, but you throw away the answer. That's not important. You take those chains of thought, and these chains of reasoning are very important. You index them and use them in a RAG kind of a setup. Okay. So in these chain of thoughts that you sort of store in your index, you could basically have this format: question, rationale, and an answer. So basically ask the model a question, the model comes up with a rationale or chain of reasoning steps, and then the final answer. You store those into your index, right? At inference time or at runtime, what do? When you get a query of this kind, this is the question, right? You basically, take the question, you give it to the LLM. LLM basically retrieves relevant memory candidates from this index. This is a large index of thoughts. It's a memory of thoughts. So it's an index of thoughts. You basically figure out the relevant thoughts or helpful memory, right? And that helpful memory goes as part of your few short prompt, so as to essentially ask the model to generate the final answer. Okay. So an extension of chain of thought, but then with RAG, and gives you better ways of asking LLMs to do annotations. Okay. Now people have, of course, also come up with other kinds of ways of doing things like tree of thought, graph of thoughts more recently. Because of lack of time, I won't get into those kinds of details at this point. Okay. Okay, so there are other ways of getting better results from models, especially when you're working in certain domains. So for example, math word problem solving. Now it might turn out that math word problem solving is not something that LLMs are good at. So what do? Okay, so for example, if you give this little simple problem, Olivia has $23. She bought 5 bagels for $3 each. So she spent 15, she's left with 8. How much money does she have left, right? She's left with 8. That's good, right? But then the chain of thought, if you really look at it, 5 into 3 is 16. Now that's bad, right? So the LLM somehow, got the right answer, $8, but with a very wrong chain of thought. Now, what can you do about this? I mean, the accuracy, of course, in this example, it didn't suffer, but sometimes it does. The final answer is also wrong sometimes. So what these guys said is that maybe I can use the large language model to take the problem and compute a program that can solve the problem. And what I can do is to basically take many such problems, and I do have answers for them. These are labeled samples, and then compute the programs, execute the program. If it basically gives me the correct answer, I save that problem and the program sample together. If it basically gives me wrong example, if it gives me right examples, I save it. If it gives me wrong examples, I basically reject that sample. Okay. So that's how I generate a very large data set, which basically contains problems and programs. Okay. Now, what I could do, of course, I've used a very large model to do this. So what I could do is to distill this to a smaller model and then use it for labeling more such examples or directly using the small language model for my purpose. Okay. So essentially saying if chain of thought reasoning does not work, you could basically try to, ask the model to generate other kinds of modalities. So rather than generating paragraphs, generate programs, or for that matter, I'll skip some slides for sake of time, right? Or for that matter, and don't generate programs or paragraphs, but actually generate logic rules. Okay. So for example, LLMs are really good at taking these kinds of logic-based problems and convert them into logic rules that just like your interpreters and compilers can understand Python code and so on. There are these logic solvers or symbolic problem solvers which can basically, like Lean, which can basically solve these problems, especially when a large language model has converted them into nice predicates. Okay. So you solve the problem using Lean Reasoner, and then you, of course, use LLM to be able to solve this problem partly. And finally, you combine the results and present them to the users. Okay. These large language models can also be used, of course, to solve symbolic reasoning problems. If you use them directly, they don't work. Okay. So therefore, one way to basically do that is to combine one task with a related task. For example, combine symbolic reasoning with numeric reasoning. Okay. So here's an example. This is basically what I mean by numeric reasoning. Adam had 5 apples. He ate 2 apples for breakfast. How many will be left if he eats one more? Now the answer is 2, and that is correct. This is called numeric reasoning example. Here is a symbolic reasoning example. The same question, but with numbers replaced by variable names. Okay, symbols, right? And then, as you can observe, the answer here is incorrect. Of course, you can pause. Later you can look at the slides and understand and look at it. That the answer is incorrect. Okay. But these guys came up with a new technique in ACL 2023, right? Self-prompting. This technique, what does it do? Well, it basically does the following. It takes Q colon, that's an input, right? And then it basically takes a numeric setup question. Numeric setup. It basically says, hey, well, here's a numeric question, right? I mean, it basically says a numeric question. Okay. And then it comes up, it basically also takes a numeric question example. Okay. Or the numeric question, right? And then basically it has a COT prompt. So as to basically tell it, hey, think step by step. So the green ones are the ones that it generates. So it basically generates a numeric response. Okay. Blue ones are what you provide. Green ones are what it generates. So it generates a numeric response. Now, after it generates a numeric response, you basically tell it, hey, now I'm going to give you a symbolic question, very similar and very aligned with the numeric sample that I gave you. Okay. And then you say, I'm starting my symbolic question. And then you give a symbolic question. And then you tell it, think step by step. And then it comes up with a symbolic response. Now, of course, you don't like the full symbolic response. What you want is just this, w minus x minus y. And therefore, what you do is to basically, again, give the symbolic question and then tell it, hey, please, can you extract the right part of the answer? I don't want the entire, explanation and COT and so on. Just give me the answer in symbolic form. This is exactly what you want, and this is exactly what you get in the green part here with much better accuracy compared to what you would have gotten if you were just doing symbolic by itself. So the self-prompting technique is a combination of symbolic and numeric reasoning to get better results. Okay. So you see, I mean, I'm almost 10 minutes sort of close to getting done. And next what I'm going to talk about is how can we use these LLMs to now also generate samples. So far, you've seen that we've used LLMs to basically, given an unlabeled sample, get the label for me. Okay. But I want to basically use these LLMs to also generate samples and then label them later. Okay. How do I do that? So let's think about it as follows. Of course, you could basically use it in the way that we have used so far, prompt-based zero-shot learning, in the sense that you basically give it to sample, you tell the model, whether the review is positive or negative. Sentiment of this movie review is what, it gives you a class label. Sure, we talked about it, and that's great. It works. Okay, on many tasks it works. Okay, but then the point is that now what I want to do is to do the other task. The task is that somebody tells me, hey, build a model for sentiment analysis. Now, I don't know how to build because I don't have labeled data. So I want to generate labeled data. I don't even have unlabeled data for that matter. Of course, sentiment analysis, you have a whole bunch of unlabeled data, but let's say in some domain, some language, you don't have labeled data or unlabeled data for that matter. Okay. I want to generate unlabeled data also. How do I do that? So I basically tell the model, hey, my class is positive or my class is negative. And the idea is that you generate unlabeled samples, or you generate some reviews. The movie review in positive sentiment is, or movie review in negative sentiment is. So you basically take the class label, encode it in some language, right? And then you tell the model, generate positive or negative samples. Once you have these samples, you basically train, and of course, you basically ask the model to also, it has already labeled, right? It has basically told you, so this is labeled data now. Then you take this labeled data, train a smaller model, and then you can deploy this model or use it for whatever purposes. So this is how typically people have used the large language models, not just to label the unlabeled data, but also to generate unlabeled data and then label it in that senses. Okay. And then people have found that, in general, if you basically, let's say, did prompting with 117 million parameters versus just zero-shot data generation, and then using just 7 million parameters and training an LSTM, you basically get way better accuracies across different data sets. Okay. So this soft data generation using these large language models, unlabeled data generation, and also getting labels for it works, right? Especially in the small model world when you don't have too many parameters in that sense. And well, there is also some way of making it work for examples, for tasks where you require multiple sentences, like natural language inference or text entailment. Those kinds of tasks require premise and hypothesis. So what you could do is to ask the model to first generate premise and then generate hypothesis conditional on the premise and so on. Okay. So people have now come up with variants of this zero gen framework. This was called zero gen. Okay. I mean, generating data without anything, zero gen, zero shot generation. Okay. People have come up with progressive generation. Now it is progressive generation. In zero shot generation, the idea is you take the prompt, you basically, verbalize your class labels and you ask your model to generate the synthetic data. But in progressive generation, the idea is you take the prompt, you ask the large language, pre-trained language model to generate responses, but then you basically take some feedback from initial generation, and then you basically you update your prompt to generate better. Okay. So the idea in progressive generation is that you do a multi-phase data generation. Okay. You use the prompt to generate some samples, and then you learn something from those samples, right? You learn which samples were really good. So you basically therefore figure out an influential subset of those samples, and then you use them to update your prompt with good in-context samples. So the idea is you generated some synthetic data, you take a part of that synthetic data, maybe 5 or 10 really good samples, influential ones as it is called, and then you take those influential samples and update the prompt with those influential ones. Now, you see, I mean, how do you really compute those influential samples and so on are details, but I'll skip them for the time being, right? But it's an iterative approach. Okay. You could also do what is called a supervision-based generation. So the idea is as follows. Let's look at the top part here, right? Let's say you are trying to do sentiment analysis. So the label is negative and you want to generate samples for the negative label, negative reviews. You want to generate negative reviews, right? So you basically give it a one-shot example and you tell it, hey, I mean, you have to generate something negative, okay? So the generator basically comes up with something negative. It is a waste of time and money. Now, when you're using this, so the data generation part is not very different. It's basically as simple as zero-shot generation. But when you're using this data to train a model, a smaller model, right, you basically do two things. One, you essentially do temporal ensembling. What does that mean? That basically means that rather than computing your loss over whatever is generated by the small model at this point, you actually keep a history of models. And then you basically try to come up with an ensemble across that history, and you compute the loss based on that ensemble label. But the second interesting thing that you do is to not really compute a loss against a hard label generated by your model. But what you do, so for example, if your model says it is a waste of time and money, and the model says it's negative, you don't really literally consider it as negative. You basically say that, well, maybe it's negative with 80% and positive with 20%. So that is what is called as label smoothing. You basically take the hard label that was generated by the model, but then smooth it out by actually distributing some probability mass, a fixed small little probability mass to other classes, and that sort of does smoothing over labels and helps avoid label noise. Okay, or helps build smaller models robust to noise in your labeled data from the large language models. Okay, and there are examples of how what kinds of data get generated and so on. Now people also do targeted generation. Now what is targeted generation? So let's say I wanted to basically generate data for this WIC task. What is the WIC task? WIC task is basically word sense kind of a task, word sense understanding kind of task. So basically the task is that, hey, if I give you two sentences, tell me whether the sense of the underlined word is the same in both the samples. She lost her keys. His key doesn't work. That's the same key, right? That's the same key. But then if you look at another example, his key broke. Discipline is key for me. Now, of course, two different senses of the word key here. Okay, that's a task. Now, if you want to generate label data for this task, how do you generate? So these guys basically call it targeted data generation, and they do it in 4 steps, as you can see it here. The first step is basically generate a list of 50 verbs. I mean, remember here, it's a very, very interesting task. You have to generate diverse data as much as you can, right? For learning small models. Okay, so you generate a list of 50 verbs or nouns which have more than one meaning. Okay, and how do you generate? Of course, using LLM call. You just do LLM zero shot call. Ask GPT-4, hey, can you give me like 50 verbs or nouns which have multiple meanings? Then you prompt it to basically, given a word, print 4 different definitions of the word, 4 different senses, 4 or fewer. I mean, but you generate multiple senses. Then you basically tell it, hey, label is true. For the true label, remember this true label. Basically, for a given word and list of all possible definitions that you have, you can give it as part of input. Print 1 definition followed by 2 sentences containing the word in this definition. Now, why 2 sentences? Because, of course, you want to create the sample with label true. When you want to create a sample with label false, you do the same thing. Given a word and a list of definitions, for each definition, print a sentence containing the word in that definition, but then you mix and match, with sentences with other kinds of, with other kinds of senses. Okay. So that's that. But then, you still want to do a quality check. And therefore, 4th step is this one, where you essentially have a self-correction meta prompt, which basically says, hey, this was the task and this is the sample. What do you think? Is it a really good sample or not? So what is the quality of this sample, right? If this 4th basically, prompt this wants to reject, just reject the sample. Otherwise, you keep it, thereby ensuring really good quality. Okay. Now, people have, of course, also done progressive sampling with few shots. So, what is being done here is as follows. Let's say you take a question and you essentially pass it to the LLM as a few shot. This is a few shot sample, and you tell the LLM, hey, generate another sample. Generate, of course, LLM, of course, generates more and more such samples, questions and answers, and so on. And then you basically, take 1 or 2 of those, generated samples, and essentially in the next stage of prompting, you actually sample from here. So the idea is as follows. You essentially have an initial prompt, you give it to the model, you generate a whole bunch of samples, you sample a whole bunch of training data in that senses. You take a few of those high quality ones and you add them to the prompt so as to basically generate more. You keep doing this iteratively. It is very much similar to progressive generation. But the point is that you could how do you sample differs, right? How do you sample from the set to bring in those samples into the in-context prompt? You could randomly sample. You could take those samples, which to take those examples which are very different from the examples you've considered so far, so as to have diverse data in your outputs. You could basically also do other kinds of sampling, which I'll not talk about. But people have explored various ways of doing this sampling. In fact, people have also explored active learning. So the idea is that, you have in-context samples and you're trying to take unlabeled data and ask the large language model to generate labeled data. Fine. But what are you generating large labeled data, this labeled data for? So as to be able to train a tiny model, right? Now, when you train this tiny model, what could happen is that there is confusion that this tiny model has. And to resolve that confusion, typically active learning used to be done using Oracle. Okay. So here, your large language model is the Oracle. So you can also generate data from this large language model based on active learning principles. Active learning principles typically basically look at confusion or confidence, right? Or confusion or diversity kind of things. So if your small model is very confused on some samples, you basically take those samples and try to get the label from the large language model. Or the other thing to do is to basically just take a very large, the entire feature space of these unlabeled or embedding space of these unlabeled data, and then, choose diverse samples so as to basically have, labels for those diverse samples and make your small model learn all across the feature space in that sense. Okay. There are results as well. Again, due to lack of time, I won't go over the results, but there are results which sort of show that this way of sort of, labeling gives you better results compared to zero-shot generation, zero-gen or progress-gen kind of approaches that we looked at so far. Lastly, let me very quickly talk about how do you motivate these models to generate diverse data. Okay. So for example, let's say you want to generate data about some sort of you want to generate data about the relation head of government. Okay. So basically, who is the president of the USA, or who is the prime minister of Italy, or who is the prime minister of India, and so on. Okay. So now to be able to do that, or to be able to generate, by the way, questions for any given relationship, any given kind of relationship on an entity relationship graph, you can do a few things. You could basically give a whole bunch of unlabeled data and ask the model to label, right? I mean, maybe it's just a binary label saying whether this relationship is present in the sentence or not. Okay. Or you could basically ask the model to generate the data. So in this kind of a setup, training data generation kind of a setup, you basically, I mean, maybe in this particular case, it could be, let's say, sentiment analysis, or it could be, well, in fact, prompted data generation. So you want to generate sentences which with a particular relationship. You would need to do two steps. First, you need to teach the model to generate head, tail entity pairs that have some relationship. And then you have to basically do another prompt so as to essentially ask the model to use the generated entity pairs and the relationship and then construct a sentence. Okay. So a way of coming up with diverse generation is to basically assist with the dictionary. So the idea could be that you can basically first use a dictionary. You can basically first query the head tail entity pairs from, let's say, Wikidata. And then once you get those entity pairs, you can basically save on this first prompt. You don't really need this prompt, right? Head tail entity pairs could be directly obtained from a dictionary like Wikidata. And then you can basically ask ChatGPT or GPT-3 or GPT-4 to actually generate outputs. Okay. Now, talking about generation, people have used this generative stuff to generate interesting things like generate personalized dialogues. Okay. So some of you might have heard about persona chat dataset. It's a very, very popular dataset about personalized dialogues. So persona in this dataset is expressed in terms of 5 sentences for every persona. Okay. So you could basically read these 5 sentences, and this is a kind of a persona. And then, what people have done manually, right? All of this was generated manually. Mechanical Turk workers basically read the persona and generated a dialogue as if they have that kind of persona. Now, can you synthetically generate this data set? And it turns out that yes, people have tried to synthetically generate this data set. They first synthetically generate the profile or the persona, and then they generate, an entire dialogue, as I can show you on the next slide. Okay. Now, of course, while doing so, you have to basically motivate the model to generate persona, is 5 different sentences which talk about a persona. For example, here I wanted to talk about a persona, of a person who likes a whole bunch of songs. Preference. It's a person who likes music, and the idea is that we tell the model to be able to generate to mimic a persona where the preference is basically Lady Gaga, and so therefore. Essentially, the model should be able to generate things related to Lady Gaga. Sometimes it does wrong things. Sometimes it basically generates other kinds of things. But many times it basically does generate nice sentences which can resonate with this profile. And then once you have this few shot persona, which is very good, you can ask it to basically, you can give a few short conversations. You can tell it, hey, for this persona, here are a few examples. But then you can actually tell it for this new target persona, can you essentially now generate conversations? And here are automatically generated dialogues. Okay. So there is a P1 and there is a P2, person 1, person 2 with their persona automatically generated clearly, right? And then there is an entire conversation which is also automatically generated given people of these two persona, Okay. Almost, I'm almost done. And what I also want to tell you here, this is basically a paper on attributed data, training data generation, and focusing on how do you get data which is diverse and not biased. Okay. So the idea is that if you basically ask the model to generate a news article, very likely it will generate news about the US because the pre-training data is so biased towards US, right? Very likely it will generate some output which is in English, and very likely it will generate an output written in the style of New York Times. Okay? Now, how do you avoid that? To avoid that, what you could do is to do attributed generation. So you could basically prompt the model to say, hey, what could be important dimensions when I'm trying to write a news article? So dimensions meaning subtopics, They could also mean, style of writing. They could mean location. So there could be many, many attributes. And then you basically give this prompt to the large language model that, hey, for these various subtopics, which have been, again, given to me via a different GPT prompt and different lengths of articles and different people, different authors who could write and different locations, can you basically now generate articles using a prompt of this kind? And if you basically do this, of course, you end up with a whole bunch of diversity because you are now going to generate articles not just from the US, but from various other countries anyway. Okay. So here are some examples. Basically, you can, of course, look at them later, but here it's generating, if you do not do this attributed generation, it generates Washington, DC based news mostly. But this attributed prompt can generate, news about various countries, as you can see, Germany, Mexico, Japan, and so on. Okay. So in summary, I talked about various things. LLMs are good annotators, but they have to be used carefully, right? Sometimes they can lead to nasty results, but you can apply a whole bunch of techniques that I talked about so as to get high quality annotations from LLMs. You can use chain of thought prompting, analogical prompting, memory of thought, program prompting, lean reasoning, reasoning kind of prompting, symbolic reasoning, and so on. You could also use techniques to generate data from these LLMs and label them high quality data. Using zero-shot generation, progressive generation, supervised generation, target-based generation, just one-shot, one-shot generation, active labeling, and so on. And lastly, to generate diverse and attribute-specific data sets, you could use these attributed training data generation techniques or diverse persona-based techniques, dictionary-based techniques. I'll stop here.